Quick, graph one period of y equals -2 times the sine of the quantity pi over 2 times x plus pi over 4 plus 1 by hand. This is part of the family of functions series. You will need paper and straight edge, and we suggest you create grids similar to the ones at the right as needed. Press pause as needed anytime during this video. We're going to graph one period, so let's go ahead and analyze this. Since the leading coefficient is negative, we will analyze y equals +2 times the sine of this quantity plus 1, and then reflect this blue graph about the line containing the points of inflection to get the one we actually want. Pause is needed. So we're going to analyze the blue graph and then again reflect to get the green one. Which parameters affect the y values in the blue equation? The 2 times and the plus 1. The times 2 multiplies each y value by 2, and the plus 1 adds 1 to each y value. And by the order of operations, remember that we multiply first and add second. And we're going to look at the y values of the points of interest so that we can multiply them by 2 and add 1. So the maximum normally is at y equals 1. We're going to have to double that and add 1 to get y equals 3. So our new maximum's at y equals 3 on the blue graph. Points of inflection are normally at y equals 0. We're going to double the 0 and add 1, and that will get us at y equals 1. The minimum's normally at y equals -1, but we double that, -2 plus 1, and we're back to y equals -1. So let's summarize that right here. These are our key y values, and you can see where we got them from. Which parameters affect the x values? That would be the pi over 2 times and the plus pi over 4. Recall that the beginning of a period normally starts when the argument is equal to 0, so we're going to set that entire argument equal to 0 and solve for x to see where this one starts. So pi over 2 times x plus pi over 4 is equal to 0. We want to solve that for x. Pause is needed to do that. We're going to multiply each term by 4 on each side to clear out the fractions. Subtract pi from each side, and then divide each side by 2 pi. And our period is going to start when x is equal to -1/2. The end of the period normally ends when the argument's equal to 2 pi. So we're going to set, again, that entire argument equal to 2 pi and solve for x. Pause is needed to do that. We're going to multiply each term by 4 again to clear out the fractions. Subtract pi, and then divide both sides by 2 pi and get x equals 7/2, where the period will end. Pause is needed. Using all the values below, let's decide how to mark off the units on the x-axis and the y-axis. We suggest that x is between -1 and +4, marking each 1/2. And we suggest that y is between -2 and 4, marking off each unit. Pause to create that. Resume when you're ready. The axes are not drawn square, but they do include all the values that we need. So let's put this all together, kind of like putting a puzzle together. Piece this all together. We're going to draw dotted horizontal lines at the maximum, the points of inflection, and the minimum, starting with the maximum at y equals 3, a blue dotted line. Points of inflection are orange, y equals 1. And the minimum in aquamarine, y equals -1. And we want to fit the sine curve in between these horizontal lines. So let's recall the graph of one period of the sine wave. We're going to start at a point of inflection, the beginning of a period, which is normally 0, 0, but for our purposes, it's going to be when x is negative 1/2 beginning, and the points of inflection are at y equals 1. So that's where we're getting those values from. And so we'll plot negative 1/2, comma 1. The end of the period is when x is 7/2, also a point of inflection 1. So you can see where we got those two values. So we'll plot 3.5, comma 1. Halfway between these two, beginning and ending of a period, is another point of inflection. We can kind of see where that is here. It's going to be at 1.5, comma 1, equidistant from the beginning and the end. Halfway between these 2 points of inflection is a maximum, so a similar thing is going to happen here. And we can see that that's going to be at 1/2, comma 3. And finally, the last point, the minimum, is halfway between these 2 points of inflection, halfway between these two, and we can see it's going to be right there at 2.5, comma negative 1. So let's plot it. Pause is needed. Now we need to reflect these points about the line containing the points of inflection, because remember, this is not the one we wanted. We want the green equation, and that negative sign is going to make us reflect it about the line containing the points of inflection, which are right here. So the points of inflection, this point will now become itself. It reflects as itself. This point that's a maximum will reflect down here as a minimum. This point of inflection will stay there. This minimum will reflect up to a maximum. And this point of inflection will stay as a point of inflection. Let's connect the green points as a sine wave. So concave up, followed by concave down, and then we'll smooth that out. Equivalent forms, we could factor out the pi/2 inside the argument there, and from that we can see that we have a phase shift left of 1/2, and we can see that happens right here at negative 1/2. The graph's sign starts here, but remember it's upside down, so to speak, because of the negative. The period is 2 pi divided by this pi/2, and that's period is 4, and we can see that from this starting point to this ending point, that is 4 units, so it double checks there. Pause is needed. Now you try one. Graph one period of this function right here. Pause is needed. And we supplied a lot of information where the maximum points of inflection and minimum are, the y values, the beginning of the period, the end of the period, the x values, and the graph.